Welcome to Reasonable Data Science, the channel devoted to teaching a reasonable amount of data science in a reasonable amount of time. This is video 5 in my series on how to use JupyterLite for data science, and I'm really excited to go over this video today because we're going to demonstrate how to build and use a linear regression algorithm. So what we're going to try and build and use the linear regression algorithm on is to predict the sale price of homes using all of the home's attributes, such as what city they're in, the bedrooms, how big is their house, etc. But before we can begin building the linear regression algorithm, we always first need to import the packages. So if you've been following along in my other videos, thank you very much. You should be familiar with the 3 packages we've loaded before, the pandas, the numpy, and the matplotlib. Some new packages we need for this video include the Statsmodels, which these 2 packages right here are going to allow us to create our linear regression model. And then we have some from sklearn here. So the first one is the test train split. That's going to allow us to build our training data set and our test data set, which we'll use later on in this video. And then we'll also have a couple metrics packages from sklearn, which those will be used to measure how good our linear regression algorithm is at predicting home prices. All right, so now if we were to look at the data set here that we've imported and say df.head, it'll show the home data set that I was talking about. So price here is the variable that we're trying to predict in our linear regression model. This could be called our target, our dependent, or our y variable. All these other variables are all the attributes of the homes that we're going to use to try and predict price. So there's the jurisdiction of the city that it's in, there's the size of the land it's on, whether it's a 2-story, a 1-story house, how big the home is, and all these other ones as well. But what you'll notice is that there's a couple key variables that are non-numeric, such as jurisdiction and residence type. We'll actually have to turn these into what's called dummy variables because linear regression models are not able to take in text data. So you need to turn any text or categorical data into what's called dummy variables. So the way that we can do that is we can use our pd.getDummies function and then specify the columns that we want to change. So we're going to say df equals pd.get_dummies. Then we're going to say df, and then I'm going to say columns equals, and these are the columns that we're going to use. We're going to say jurisdiction. We're going to say residence type. Make sure to put them in quotes. And then the last one we're going to change is bedrooms. And bedrooms looks like it's a numerical value, but it's actually a categorical value when you think about it. You can only have a 1-bedroom house or a 2-bedroom house. You can't have a 1.5-bedroom house. So you have to make sure you turn bedrooms into a categorical variable. Then we're going to say drop_first equals false. I want all the values for all the dummy variables in the columns. And then the last we're going to say dtype equals int. And so when you run that, you won't actually see anything. But now if you were to say df.head and run this here, you'll notice that our jurisdiction column, which was first, is no longer first. Instead, it actually got broken into 3 different columns here: a column for city A, a column for city B, and a column for city C. So how the getDummies function works is that it takes every unique category and pushes it to its own column here. And then if you see a 1 in that column, that means that this house belongs to a city C. If you see a 1 in column B, that means the house would belong to city B. And we did the same thing for residence types. It created 2 new columns for that, and it created 3 columns for bedrooms. So it looks like we only have a 3-bedroom, a 4-bedroom, and a 5-bedroom home in this data set. So very important concept before you run any sort of linear regression algorithm, you always have to turn your categorical variables into dummy variables. Otherwise, you won't be able to run your regression algorithm. So after we have set up our data set, made sure we've created dummy variables, we can now set up what's called our training and our test data sets. So what we're going to build is a data set called train, and we're going to randomly grab 80% of the rows of our data set and put those rows into our train data set. And we're going to use that train data set to train our linear regression algorithm on. The remaining rows, or the remaining 20% of our data, we're going to put into a test data set, which we're then going to use the linear regression model that we built on our training data set and apply it to that test data set, and then see how accurate our model predicts that testing data set. So to set up our training in our test data set, we need to specify our y and our x variables. So I'm going to say y equals df of price, and I'm going to say x equals, and what you could do is you could type in every single column you want in here. That's kind of a time-consuming way to do it. So what we can do is we can say, I want to grab all the columns to the right of our price column, let's say. So I'm just going to say df dot I loc. I'm going to do colon 1 colon and then this. And so if we were actually to look at this real fast before we run it, just to make sure it works right, what this is going to do is it's going to return all the columns to the right of the price. And it looks like, oh, instead of using 1, we actually need to use 2 because we included price in our X data set. We don't want that. So we're going to say 2 here. So now when we say 2, it returns all the columns to the right of our second column here, which is price. And so up here, we'll change that to a 2 and run this. So now if we were to look at y.head, you'll see that's the price column. If we were to look at x underscore or x.head, that's all the columns excluding the price column. So we've set up our x and our y data sets. Now that we've set up our x and our y data sets, what we need to do is create our training and our test data sets. So the function we're going to use is called test train split function. So what this is essentially going to do is going to create 4 new data sets. So it's going to create a data set called x underscore train, x underscore test, y underscore train, y underscore test. And so this function is going to create 4 new data sets, 2 trainings and 2 test data sets. So we're going to say train underscore test underscore split. And what we're going to be splitting is our x and our y that we created up here before. And then what we're going to say test underscore size equals 0.2. So what that's saying is that for these 2 test data sets, we're going to be randomly grabbing 20% of the data and moving them into our test data sets. The 80% of the data set remaining is going to be pushed into our 2 training data sets here. And then last thing we want to do is we want to say random underscore state equals 0. And that's really important to specify because if you ever want to go back and create the same exact data set, all you have to do is say random state equals 0. And then that would create the same random split. If you don't do that, you'll never be able to go back and create the same random split ever again because it's random. So we run this, you won't see anything, but what we can do is we can actually look at our 4 data sets. So we can say y underscore train dot head. So this is going to be the y variable in our training data set, which is price. We're going to try and predict our price variable. If we were to say x underscore train dot head and run that one, that's all of the columns excluding price. And since we said 80% of our rows need to go to the train, if we were to say x underscore train dot shape, we get 32,594 rows. So that should be 80% of our overall data set. So if we said df dot shape, and then we were to just say 32,594 divided by 4743, we get 80% of our rows are in the X-train data set. Y-train should also be the same. If we were to go up here and change it, we'll get the same 32,594. If we were to say, what's our y-test data set instead, we get 8149. So that should be, instead of 80%, should be only 20% of our data set here, which it is. So it looks like we created our training and our test data sets correctly. So again, our training data set has 80% of the rows of our data. Our test data set has 20% of the rows in our data set. The next thing we're going to create is our linear regression model. And so I always like to start out just with a very simple one variable linear regression model. And I always like to try and choose the variable that I think is the most important in the data set. So when it comes to homes, I believe the size of the home is the most important variable to explaining the price of the home. So the bigger your home usually is, the more expensive it is, right? And so let's add this total living area as our first variable in our linear regression model. So I'm going to create a new variable called linear model, and this is what we're going to put our linear regression model output into. And we're going to say sm.ols. And I'm going to say y_train. And then we're going to say sm.add_constant. And so this y_train is the is our y variable price from our y_train data set that we created up here. We're then adding this constant value, and we're going to say x_train, which is our x_train data set. And then within there, we need to select the columns that we want to use. So we're going to use total living underscore area first. And we're going to do two parentheses, and then we're going to say dot fit. So we're fitting this model. We're building a model that's going to use the total living area to try and predict our price variable. And then if we were to say print linear model dot summary, open and close parenthesis, if we run this, we'll get a really nice regression output. So the first thing I always like to check is what's the adjusted R². So the adjusted R² for this model shows 52.6%. So what that tells us is that this one variable, total living area, explains 52.6% of the variation in our price variable. That's quite a lot for just the one variable. So it seems that total living area is a very important variable to try and predict the price variable. The second thing I always like to look at is if you scroll down here to the coefficients. And the first one you'll notice is a constant, which you can pretty much ignore that for this model. But what the constant is the y-intercept. That's another name for it. And it essentially shows the value of a home when the total living area is 0. Since we can't have a home with 0 total living area, the constant in this model can be ignored. But what is important is the total living area coefficient of 138. So what that means is that for every one incremental change in the value of total living area, the price of a home changes by $138. So if you add an addition to a house and increase the total living area by 1 square foot, the price of your home would go up by $138. If you somehow removed 1 square foot from your home, the value of your house would go down by $138. I don't really like sometimes the output that this coefficient table shows because, as you can see, it has scientific notation. I hate scientific notation. So what I like to use is this function called linear model.params. And again, remember, linear model is just what we stuffed our output into. And then using this .params function, this will just return a nice non-scientific notation looking coefficients here, especially for the constant value. So how can we use this regression model that we built to predict our home price? If you remember, regression models are just using the slope of a line for their equation. So the slope of a line is y equals mx plus b, right? Where b is the constant here in our equation, and the m is the value of our total living area, and the x would be whatever the size of our total living area would be. So if we just said linear model do a parenthesis here. If we just said linear model dot params dot iloc, and then said 0, and then we took that plus linear model dot params dot iloc of 1, and we took that times 2000, double parenthesis. What that's going to do is going to take our first value of our params function here, which is a constant, which is also the b here. We're going to add onto it the first coefficient of total living area and take that times 2000. So essentially we're wanting to predict a 2000 square foot home. So if we were to run this here, our model says that for a home that's 2000 square feet, the price should be $264,000. But how accurate is that estimate? Well, there's always some sort of error around every estimate for any algorithm. So the way we can look at the error is we can say np.square root linear model.scale, and we'll get an error estimate of $72,000. So essentially, our estimate here could be off plus or minus $72,000. And so really the true value of a 2,000 square foot home lies within that range of $264,000 plus or minus $72,000. So that's how to build a linear regression model with one predictor variable here. But let's try and add in a couple more variables to see what happens. So if you want to add in a second predictor variable, you just come up and use the same equation we built before. Make sure to add in double brackets here. And we're then going to say att underscore garage underscore area, which is the attached garage area of a house. And make sure to add double brackets on the side, on the back end here. When we run that, we get the same output, but you'll notice that the adjusted R squared value now went up. So adding the size of the garage to our linear regression model improved the R squared by about 7 percentage points. When we look at the regression coefficient outputs here, it looks like total living area, its estimate went from 138 down to 95, and the attached garage area actually came in at 120. So it looks like in our model here, if you were to add on to your garage, that actually provides more value to your house than adding on, more square footage. In theory, that doesn't really make sense. So what's probably going on here is there's some funkiness in the data, which hopefully we can iron that out a little bit later when we add more variables to the model. If we wanted to then predict a 2,000 square foot home with a 400 square foot garage, we could just use the same function we had up here and just add a new term to it. So we can just say plus linear model dot params dot iloc of 2, take that times 400. And when we run that, we get a new estimate of 253,970. So this is now showing that a home with 2,000 square feet and a home with a 400 square foot garage should sell for about $253,000. If we want to check how good that estimate is, we could just say np.square root linear model.scale. And it looks like our error metric actually went down from 72,000 to 66, which is good. But again, you'd still have to add plus or minus this value to get our true range of where a 2,000 square foot home with 400 square foot garage would lie. All right, so that's how to build a linear regression model using numerical values. But if you remember, if we were to look at our data set, we have non-numerical values in here. So we have city and we have residence type as well. What if we wanted to include those values in a linear regression model? How would we do that? Well, we would do it the same way as we did up here. So I'm just going to come up here again and copy our linear regression equation. And if we wanted to add, let's say we wanted to add the jurisdiction in to our model, we would just type in those variables into our model here. But just a word of caution. So whenever you're using dummy variables in a regression model, you always need to exclude one of the variables. So since we have 3 jurisdiction variables here, we're only going to put 2 in our model here because that third one is going to be what we refer to. And so I'm just going to come up here and just copy jurisdiction city A. That way I know I spell it right. And then I'm going to copy jurisdiction city B. And I'm not including city C in the model because city C is going to be our reference column or our reference city that we're going to compare city A and city B to. So let's just run this and look what this looks like. So the first thing, our adjusted R squared went up a little bit, not too much, but when it did go up some. When we look at total living area, it looks like the estimate was changed just slightly. Total or attached garage areas coefficient changed slightly. And since city A and city B are now in our model, we can look at those coefficients, but they're in scientific notation. So I'm just going to go like this, linear model.params. And let's just look at a nicer output. So what this is showing is that when we look at just city A looks to sell homes for $13,922 more than city C does. So city A homes are priced higher than city C homes. How I'm getting that again is we excluded city C from our model here, so city C is our reference variable. City B looks to be selling homes for $9,200 more than city C does on average. And so that's how you can read the dummy variables in your model is you always exclude one of the dummy variables, and then the dummy variables in the model are always in relation or reference to that one you excluded. So if we wanted to then predict, let's say, a 2,000 square foot home with a 400 square foot garage in city A, we can just add on to our equation we built here before. So I'm just going to add plus, and I'm going to do linear model.params.iloc of 3, which this is the third variable here. And I'm going to take that times 1 because if we remember up here, if we scroll up, the cities are just ones and zeros. So anytime there's a 1, that means the value's in that city. Whenever there's a 0, it means it's not in that city. So if we want it to be in city A, we just take the coefficient times 1. And then to be thorough, we're just going to add in linear model.params.iloc of 4. And we're going to take that times 0. So we're taking this coefficient times 0 because our home is in city A, not city B. So if we run that, we then get an estimate of a home that is 2,000 square feet, 400 square foot garage in city A, looks like it's $260,000. If we wanted to test out what is the value of a 2,000 square foot home with a 400 square foot garage in city B, we can just copy the same equation. And instead of using a 1 on city A coefficient, we're just going to flip that to a 0. And instead, we're going to use a 1 on cities B coefficient here. And we're going to run that. And so the value of a 2,000 square foot home with 400 square foot garage in city B now is $256,000. So it is less, which makes sense because the coefficient for city B is less than the coefficient for city A. Now here's kind of the tricky part. Let's say we wanted to test what is the value of a 2,000 square foot home with a 400 square foot garage in city C. What would we do? Well, it's not in city A, so we're going to make city A's coefficient 0. It's not in city B, so we're going to make this one also a 0. And so when both city A and city B coefficients are 0, we're going to say then that house is in city C. And so when we look at that, it's 246,806, which city C is less than city B, and city B is less than city A. So all of this makes sense so far when we include that city jurisdiction in here. We can just keep going with our W variables too. So if we said df of head and we looked at what else we wanted to include in here, if we wanted to look at what is the relationship also between one-story and two-story homes, we can add that in as well. So again, I'm just going to come up here, copy our linear regression equation. And then I'm just to make it easier for you to read, I'm just going to put these down on a new line for all of these ones here. And then I'm just going to copy residence one story. Because remember, residence type has two columns, so I'm excluding the two stories from my model and only using one of the variables. So therefore, when we look at the residence story, it's going to be in relationship to this two-story value here. So if we run that, looks like I got an error on there. Maybe I'll just bring it back up here. I'll just undo that real fast. I'm just going to copy that up here. There we go. So it's a little long to see, but it looks like it should work for us. I'm just going to go copy again and redo it here. There we go. So let's just add in the residence one story here. That we'll run that here. And we get an output. There we go. And so the one thing you'll notice is that adding in the residence one story variable jumped our R squared, or just R squared, up from 59 to 65%. So it looks like it's a very significant variable. But again, these coefficients are in scientific notation. So let's just look at them outside of scientific notation. So we're going to say linear model.params. And so when we look at it, it looks like residence one stories, so homes that are one stories, sell for on average almost $60,000 more than a two-story home. So if we wanted to estimate what is the price of a 2,000 square foot home with a 400 square foot garage, and let's say in city A, and it's also a one-story home, we can just add on to the function that we created here, or the equation. So I'm going to say linear model dot params dot iloc 5, because residence one story is 1, 2, 3, 4, the fifth one. And then I'm going to take that times 1 again. And since we want to look at what's city A, we then change this one to a 1 again. And so if we have a 2,000 square foot house, 400 square foot garage in city A, and it's a one-story home, it looks like it sells for $304,000. If we wanted to look at the same home, but it's a two-story house, we would change the one-story coefficient to a 0. So we're going to just take it times 0 here. And when we run that, we should get something that's around $60,000 less than the home of a one-story in city A. All right, so if we wanted to test what the error is on our new model with all of these variables that we've added to it, we can just use the same function, np.square root linear model.scale. What we should see is, since we've added a lot of significant variables, that the error on our model has actually been going down. So remember back when we only had total living area in our model, our error was about $72,000. Now that we've added all of these significant variables to it, our error has dropped to $61,000, which is what you expect to see when you add significant variables. The adjusted R squared goes up, the standard error goes down on a model. So it looks like our model's starting to look pretty good, but how we can really test how well our model is at predicting new data is we can use our test data sets. And so we're going to use our X test and our Y test data sets to create, to apply our new model to those data sets and then see how well they predict that data. So if you remember, our Y test data set is just the price, and it's only 20% of the rows, and our X test data set has all of these columns in it. So what we need to do is we're going to just apply our linear regression model to using these X and Y test data sets. So I'm going to set this up and I'm going to say Y test and then say predicted. So what we're going to do is we're going to add a new column to our Y test data set here. So if we look at that again, we're going to add a new column next to price called predicted. And so what this is going to do is we're going to use our regression algorithm and to try and predict every one of these rows in our y-test data set and then see how close we get to predicting those ones. So we're going to create that new column in the y-test data set, and then we're going to say linear model.predict, and then we're going to say sm.add underscore constant, and then we're going to say x underscore test and double brackets. And make sure when you use this, you only use the variables that we've included in our regression model so far. And so I'm just going to come up to here, what we did before, and just copy all of the variable lists here. And then I'm going to paste that in. And just to make it easier for you to see, I'm just going to add these to a new row, just so it's easier for you to see. And so again, when you're trying to predict using the test data sets, make sure you only use the columns that you've included in your regression data set. Otherwise, you'll get an error when you go to run this. And so if we just close it off with two brackets and then two parentheses, that will then, this function right here will then predict all of the prices in the y-test using our regression model that we built. So if we run this, we won't see anything. What we can then do is look at our y-test data set, y-test.head, and we now have a new column in that data set. So next to the price, which is the actual price that we're trying to predict, we have a predicted column, which is what we created up here. And as you can see, when you look at just these first 5 rows, the price of this home was $165,000. Looks like our model predicted $163,000. The price was $216,000. Looks like we predicted a price of $234,000. So overall, when we look at these first 5 rows, our model with just these variables in it looks like it's doing a fairly good job of predicting the price so far. But what we can really use to measure how well it predicts all of the rows is we can use the mean squared error, which it will basically just take and look at what's the difference between the predicted and between the predicted column and the price, and then sum that up and average it over the whole entire data set here. So if we say np.square root, and then we're going to use the function mean underscore squared underscore error, and then we say y underscore test of price, which is the column here. And then we say y underscore test of the column predicted, which is that column here. Close that off and then double parentheses. When we run this, we should get one number. And what that number shows is the testing error of our linear regression model. So when we compare all of the predicted values to the price value, on average, our model has a testing error of about $60,000, which is really close to what that standard error was before. But this is a more legitimate way to measure how well our linear regression model is performing against data it has never seen before. We could continue to add in more variables since we have numerous variables in our data set to try and get this testing error down even further. It's definitely possible. But for this video, we've demonstrated how to build a linear regression model, how to use a training and test data sets to get a pretty good estimate of home prices. So thank you again for watching, and please like and subscribe to my channel if this video was helpful to you.